Let's go to page 589. This is lesson 9.3. This lesson is to perform reflections. It says in lesson 4.8, you learn that reflection is a transformation that uses a line like a mirror to reflect an image. So again, this is a line of reflection. So image, so you flip this over. Okay, the mirror line is called a line of reflection. So again, this line like mirror, acting like mirror, is called a line of reflection. A reflection in line M maps every point P in a plane to a point P prime. So that for each point, one of the following property is true. If P is not on M, then the M is the perpendicular bisector of P prime. So again, if this is not on a line, so when you connect the P and P prime, okay, this would become the perpendicular bisector. So what that means is that when you connect the two lines, right, connect the 2 points, P and P prime, okay, this is going to be the right angle, and also this will be congruent, so the same length, okay. So P to the line is equal to the P prime to the line. So again, you have to be exact, right? Imagine if you fold things over, right? You have to be exactly, okay. And if the P is on the M, then P equal to P prime. So again, if the points on the line, when you reflect, it would be equal to itself. Okay. Okay, now let's go to example 1. It's a graph reflection in horizontal and vertical lines. So it would be helpful if you use a graph paper, and it makes things a lot easier. Okay. It says the vertices of triangle ABC. So that's a blue triangle. Okay. It's a blue triangle 1, 3. So you can see here 1, 3. Okay, so that's that. B is 5, 2. So you go 5, 2. Okay. Okay, so I'm going to use this. So 5, 2. So you go 5, 2, and 2, 1. So you go 2, 1. Okay. Now it says graph the reflection of triangle ABC described. Okay, so first you plot that, right? Okay, now they give you 2 different parts. So first you want to do the line of reflection x equal to 3. So x equal to 3, that's your line. Okay? Okay, so here's your line. So now you're going to reflect over that. So the way you're going to do that is, notice this line. So point A is 2 units from the line, right? 2 units. So when you reflect over, you will go 2 units this way. Okay, so again, if you notice over here, so from here, right? So you got 1, 2, right? So when you reflect over, you go to opposite direction because they have to be the same distance. Okay, and that's your A prime. Now B is over here. B is 2 squares or 2 units from to the right. So when you reflect over, it becomes 2 units over here. Okay, so just flip it over. The C is 1 unit. Okay, 1 square. So when you go over the other side, it would be over here. So it would be C prime. Okay, and so that's your A prime, B prime, C prime. So flip it over. Okay. Now so for part B, so again you have the same triangle, right? The ABC, so ABC. But right now the line of reflection is right over here, the green one, the M. So when you're doing a reflection, again here's your line of reflection. So notice right now the A is 2 units above, right? So when you reflect over, it becomes 2 squares below. So you can just count the square, right? So 1, 2, so you go down 1, 2, right? This one is 1 square above. So when you flip it over, it becomes 1 square below. They have to be the same amount, okay? So again, you have to pay attention to the line of the reflection. Now point C is on the line, so when you reflect, it will stay on the line, okay? So it's just a matter of, pay attention to, counting the squares, okay? And again, make sure you draw the nice picture. Don't get sloppy because that's going to easy to make careless mistakes. Okay. So use a ruler. First you plot the 3 points. Use a ruler to draw a nice triangle. Then after that, you just go and count the squares and flip it over. Count the square, flip it over. Okay. Okay. Now let's go to example 2. It says graph of reflection in y equal to x. Okay. It says the endpoints FG, so you got FG over here, are -1, 2, and G is 1, 2. Okay. Reflect the segment in the line Okay, so you're going to reflect over this now. Okay, so graph the segment in its image. Okay, so you can remember everything is perpendicular, right? So perpendicular in this case is going to be like this. Okay, so again, so when you have the line of reflection, you do the perpendicular and you flip it over by the same amount. Okay, so you can use a ruler to measure. You can count the square. So this is so from here to here, it's like half of the diagonal. So from here to here, it'll be half of the diagonal of the square. Now from here, okay. So how do you know it's perpendicular? What you do is using the marking. See like this over here. See, that's how you. So this is your diagonal. So you line up the edge, okay, and then you slide it over. Or you can use the marking. See the marking over here, okay. Or you can just look at the square. See over here. See you connect. See over here. See the corner, the corner, the corner, the corner. That's how you line it up, okay. And so again, you can use the ruler to measure. Or notice you got one diagonal and a half, right? So 1.5 diagonal of the square. So 1.5 diagonal of the square. So over here. Okay, or you can use a ruler to measure, or you can count the diagonal. So so this one a little bit harder. Okay, now when you do the reflection, you also can do it by coordinates. So here's your summary. Okay, so make sure you know this. Okay, so when you reflect over the x, okay, so x, here's your x-axis. Right? When you reflect over like that, so when you reflect over, the x stay the same. The y get opposite. So again, when you flip over, I think like this, right? So when you reflect over, when you reflect from here to here, okay, the x does not change because you're going up and down. The x stay the same, but the y become opposite. Okay, and the others now when you reflect over the y-axis. So if this is the y-axis, okay, so let's do this. So if this is the y-axis, so when you reflect something over, okay, notice when you switch over, the y stay the same. Okay, when you flip over, the y stay the same, but x change. So y stay the same, the x become opposite. Okay. Now when you reflect over the y equal to x like this over here, okay, when you reflect over that, what happens is that you switch a and b, the x and the y. Okay. So if you notice, see this point over here is 1, 2, right? It becomes 2, 1. Okay? This point is -1, 2, and it becomes 2, -1. So the coordinates got flipped. Okay? Okay. And now when you reflect over the y equal to -x, that's this case right over here. So this is this over here. So when you reflect over diagonal like that, you switch x and the y. When you reflect over this way, you switch x and the y, and you times by -1. See that? Okay. So if you remember your logic, okay, this is like a contrapositive. This is like the converse, right? You switch x and the y, and this one is your converse and the inverse, right? That contrapositive. So you switch and you times by -1. Okay. So again, in this case, you switch x and the y coordinates. This one you switch x and the y and you times by negative. Okay. So this is your summary of what happened with the coordinates. Okay. Now, if this is confusing, okay, a lot of times it's easy if you just graph, and then after you graph, you flip, and then you write the coordinates after that. Okay. But this is important to know because the more things you know, it makes things a bit easier to solve problems. Okay. Okay, now let's go and do this one over here. So you got FG from example 2, and you want to reflect over the line y equal to -x. Okay, so again, right now, you just do the same thing, right? You remember, you just do the perpendicular. And since the lines, what you do is you line up the corner of each triangle. The corner of each square. Okay, that's how you know. Okay, and again, from here to here, that's half of the diagonal, so it'd be right over here. Okay, now this one over here, again, you line up, use a ruler to line up the corner of every square. Now this is one diagonal and plus half, so you're going to be half and one diagonal. That's how you locate that. Okay, now if you do it by coordinates, okay, again, if you do it by coordinates, the point F, the point F is -1, 2. Okay, and G is 1, 2. Okay, so F prime would be first you switch, okay, and then you times by negatives would be -2, +1. Okay, so this one again, you switch, and then you do the negative. Okay, that's how you get the coordinates, and you can check, right? So this is, see over here, -2, 1. This one is -2, -1. Okay, so that's how it works. Okay, by using this over here. Okay, so again, you can, depends on the situation. Sometimes it's easier one way, sometimes easier is the other way. So you can either flip, then get the coordinates, or you can do the coordinates and then do the graphing, the flipping. Okay. Okay. Now let's go to page 591. Okay, reflection theorem. Okay, you saw in lesson 9.1 that the image of the translation is congruent to the original figure. The same true for reflection. Okay, so when you flip things over, the shape stay the same. It's congruent. Okay, so the reflection theorem. A reflection is an isometry. Isometry means iso means same. Metry means measurement. So same measurement means they're congruent. Okay, so again, when you're doing the reflection, it's congruent. Okay, okay, prove the theorem. Okay, so to prove the reflection theorem, you need to show that a reflection preserves the length of a segment. Consider segment PQ. Okay, that reflection on the line M produce P prime Q prime. There are 4 cases to prove. Okay, so you can have the PQ on the same side. You got PQ on the opposite side. You got PQ with point over here, and you got PQ this way. Okay, it's 4 different situations. Okay, and so again, there are 4 cases. Okay, and we're not going to do the proof, but again, notice that each case it's always perpendicular bisector. Okay, so you can you can do that. We're probably going to do that later on. Okay, but anyway, so example 4. Okay, find the minimum distance. Parking. Okay, you are going to buy books. Your friend is going to buy CDs. Where should you park to minimize the distance that both will walk? Okay, so solution, reflect. So here's your A and B. Okay, and here's a store. So to find the minimum distance, what you do is reflect one of them. Okay, so here's a store. Okay, so what you do is reflect this, and you draw a continuous line, and then that's your point. Okay, so what this means is this. Okay, here. So here is the store, and here's person, and here is another person. Wait. No, back up. Okay, so it's B. So here's one store, and here's another store. Okay, and so here's all the parkings. So where can you park so that it's a shorter distance to the 2 stores? So here's your store A, here's your store B. So where can you park? Okay, and the trick to that is what you do is do the reflection. Okay, so what you do is you can reflect either one. Okay, so over here, then you do the measure. So this is 17, 34. So here's your B prime, and then what you do is you connect the 2 line over here, and this is where you're going to park. Okay, so this is the parking will give you the minimize the 2 distance. Okay, so that's where you're going to do the parking. So you can got 2 stores. Okay, you can choose any one of the store to reflect, and you connect the 2 dots, and that's the best place to park to minimize the distance. Now, what happens if you reflect this one? You're going to get the same thing. Okay. Okay. So if you reflect this one, so if you reflect this one and you connect the dots, you're going to get the same answer. See that? So if you reflect, you connect the dots, you end up right over here. If you reflect this one, you draw again, you're going to get the same result. So this is where you park to minimize the walking to the two stores. Okay. So that's the purpose. That's kind of the practical use of the using the reflection.